Bolt is a required tool for a modern world. It is used in everything from buildings to automobiles. Today we will focus on its use in the stanchion that holds up the bridge between DC and E3.
The bolt used is approximately 7 inches long and is used to secure the stanchion in place in order to ensure there is minimal movement due to external forces. There are 4 stanchions holding up this bridge, with 4 bolts located on each stanchion.
The bolt was designed to work outside in all weather conditions, so in order to avoid corrosion it was painted to ensure no water or other electrolytes were able to enter the crevice between the nut and the bolt in order to avoid crevice corrosion. However, it can be clearly seen in this photo that paint has long flaked away, leaving room for water to enter, especially where the nut and bolt meet. It is likely that the bolt used in the actual construction of the bridge was a plain carbon steel, such as AISI 1045, as this is a typical material used in bolts. The bolt material was likely chosen due to its very low cost and high strength. The foot of the stanchion would collect water and it would easily get between the threads of the nut and bolt and cause rusting.
Bolts are typically made by the following method. First, a long round bar with the same diameter as the major diameter of the bolt is either sheared or cut to the desired length. Then, the head of the bolt is hot forged to the shape. Then, the threads of the bolt are either cut or rolled into bar. Depending on requirement, the bolt may be hardened and tempered to achieve the desired strength. Often, the bolt is galvanized to improve corrosion resistance, or left with an oxide finish if it was heat treated. Finally, bolts are cleaned to remove any oil or organic material from the fabrication process.
To determine the force the bolt should withstand, we made the following assumptions. The first being that the 4 bolts on each of the 4 feet of the bridge would be the only bearers of the load, and the second being that the bridge is massless. To estimate the force applied to the bridge, we determined the highest wind speed in Waterloo in the last 50 years, which was 120 kilometers per hour. We then determined the stagnation pressure caused by that wind perpendicular to the bridge over the area of the bridge, and assumed the force would be concentrated at the top of the bridge to get the worst case loading on the bolts. We then multiplied that force by 2 to have a safety factor of 2 in our results. We also determined that a requirement of a bolt is high stiffness. The bolts should not bend when loaded in shear.
From this, we decided upon 7 functional requirements considered in the design of the bolt. These being, must be able to withstand a tensile load of 72 kilonewtons, must be able to withstand a shear load of 11 kilonewtons, must have a stiffness of at least 1.1 times 10 to the 10 newtons per meter, must not fail by shearing the threads, must have at least 5% ductility, must be possible to hot work, and it must not corrode in 50 years, which is the typical life expectancy of a building.
Using the actual bolt's diameter of 1 inch and nut height of half an inch, it was determined that the bolt would fail from tension at a lower force than the force causing the threads to shear off. Using the approximation that strength in shear is 0.6 of that in tension, it was determined that the bolt would fail in tension before it would shear. Thus, the shear and thread shear requirements can be reduced to one requirement that the bolt be able to withstand 71.667 kilonewtons in tension with a safety factor of 2. The requirement on ductility is to ensure safety. It's very important to ensure that the bolt deforms when under extreme force instead of snapping. This allows the deformed bolt to be replaced before it causes a safety concern. As bolts are typically produced by hot working, the selected material must be suitable for hot work, or else much more material will have to be cut away to form the head. Finally, corrosion should be considered when fabricating a part to be used outdoors, as over time the mechanical properties could degrade.
In addition to these functional requirements, there are several constraints to consider in the design and fabrication of the bolt. Some general constraints are that each bolt must cost less than 50 cents in materials. This is based off a bulk price of $5 per bolt and an estimated total manufacturing cost of $2.50, of which 20% is materials. We also have the constraints of each nut and bolt must mate together, and it must correspond to standard sizes. Well, some geometric constraints based on the current setup of the bolt are that it must have a length of 7 inches, and it must have a radius less than 3 inches, so that it fits in the existing stanchion.
It was determined that the objective of this material selection would be to minimize cost. Increased weight or size would not be a concern as part of a building, so the least expensive part meeting requirements will be used. To meet the functional requirements of strength, a high ratio of specific strength to cost per unit mass is desired, with a minimum ratio of 25,484 in units of Pascal meters cubed over Canadian dollars. To meet the stiffness requirements, a high ratio of square root Young's modulus over density over cost per unit mass is required, with a minimum ratio of 9.43 in units of pascals to the 0.5 meters cubed over Canadian dollars. From this, the equations for the line representing the functional requirements were determined. After these MPI were applied, all materials with less than 5% elongation to failure were eliminated, as well as those deemed unsuitable for hot work. All remaining materials meet the minimum functional requirements.
Several other limiting conditions were applied to further reduce the number of possible materials. Since the threads of the bolts are commonly cut, all materials with machining speeds less than 10 meters per minute were eliminated. The threads of the bolts should also have good wear resistance, so all materials with Vickers hardness less than 278 were removed. 278 Vickers hardness was chosen because it is the minimum range of hardness specified for a SAE grade 5 bolt. Most of the materials that met the requirements were low alloying steels like 1030, 4140, and 5160. Several stainless steels also met the requirements. Since the goal was to pick a material that would perform better than the existing bolt in the stanchion between E3 and DC, a stainless steel bolt was chosen as the substitute so that it would have better resistance to corrosion, which is a functional requirement. Since all remaining materials met the requirements, the cheapest stainless steel that was rated as not susceptible to galling or stress corrosion was chosen, which was 431 stainless steel, tempered at 260 degrees Celsius.
A potentially better material choice would have been 431 stainless steel due to its better resistance to corrosion while still meeting the requirement of low cost through its high strength to cost ratio. There were numerous plain carbon and low alloy steels that also met the requirements, including 1045, that would result in a cheaper bolt if corrosion wasn't a concern. Over years of exposure, corrosion in the threads between a nut and bolt can make it impossible to remove. This may be acceptable for some applications where a structure is permanent. However, the goal of the project was to choose a better material, and 431 stainless met all of the requirements and offers a significant improvement in corrosion resistance for only a slight increase in material cost. Non-stainless bolts can also have treatments applied to the surface to prevent corrosion, like galvanizing or painting. However, paint chips away easily, and galvanizing can't protect a steel forever, especially in between the threads of a bolt and nut, where the coating can be worn away and crevice corrosion can occur. A stainless steel bolt will resist corrosion better than non-stainless steel over the lifetime of a building. A 431 stainless steel bolt could be made using the same process as a plain carbon steel bolt. 431 stainless is possible to hot work. The head could be formed by heating using an induction furnace to between 1150 and 1200 degrees Celsius and forging into the correct shape using dies. 431 stainless can air harden to a degree, which could make cutting threads after forging more difficult. However, if the heat is localized in the head, the area where the threads are cut wouldn't be affected. After forging the head and cutting the threads, the bolt would be hardened by heating to between 980 and 1065 degrees Celsius, held for half an hour, and quenching in oil. Then the bolt should be tempered to about 260 degrees Celsius, twice to improve toughness. Finally, the bolt should be pickled to remove oxides formed at high temperature.
From this analysis, it is clear that 431 stainless steel will be a good choice of material for the bolt that secures the stanchion between E3 and DC, due to its relatively low cost, high strength, high stiffness, and good corrosion resistance.